Today we're looking for positive integer ordered pair solutions to this radical equation. And just to make sure you're comfortable with the notation here, I'm using n in the sense of positive integers. And so say, for example, 0, 14, okay, is not a member. Okay, not a member of the natural numbers crossword. This is sometimes called the Cartesian product, I think. Okay. So we're just looking for positive integer ordered pairs that satisfy this condition here. Now, you could square away on this. There's another approach I think that's better. Notice that the 6655 is divisible by 5 and 11. You may remember the alternating series test where you alternate. You get 0 when you alternate these things in sum, so that means it's divisible by 11. Now, when you do the work, you'll see that 6655 is equal to 11 cubed times 5. Okay? Now, that turns out to be a useful structure in terms of the prime factorization, because we can see, you can write it like this, folks. See, you can write our original equation like this, because remember, this is equal to 11 squared times 11 times 5, right? So that's exactly where this comes from, and then you square root it, of course, and you get this statement right here. So the prime factorization gives us something that gives us a little bit of hope, because there's a bunch of different ways you can have 11 times root 55. One would be like this. There's an understood 1 right here, right? 1 plus 10 is 11, 2 plus 9 is 11, 3 plus 8 is 11, 4 plus 7 is 11, and 5 plus 6. Now, y'all, well, what we're doing, we're going to find the solutions here, then just multiply by 2, because this would go out even further. This would go out to 6 plus 5, 7 plus 4, and all the way out. But I'm just going to argue symmetry without having to write down everything. Now, so right here, I'll just write down the ordered pairs directly underneath here. The ordered pair that would correspond here, and let's write it like this, MN, okay? And you can almost just read it off, okay? 55 goes here, right? Because, well, that's the square root of 55, and there's the square root of M. So 55 is the M coordinate. Now, when you square this object right here, this guy right here, you would get 5,500, and that's easy to see, right? 5,500. So 5,500 is our first solution. 55 and 5,500 is our first solution. Notice we're doing all this without having to square this and do the usual stuff they teach you in high school algebra. Okay. Now, also this one is, I'll just write them all out for you. The next one would be 220. You can see we're just squaring these objects so we can write them as integers. Okay, comma 4455. Like that. Okay. Now the next one is 880, 2695. I got them written down, so I don't have to calculate them. This is 880 right here, 2695. Okay, and then the next one, I may have got these out of order, folks. I'll just write the correct one. Yeah, I got these out of order. This one right here would be 880, 2695, and I'll write 490, and I got it backwards, folks. Just remember that. I'm not going to take the time to erase it. 495, 3520. Okay, folks. And again, these are reversed. I just had it written down wrong on my paper. Okay, this one and this one should be reversed. And finally, the very last one, I think I got it right, would be 1375. 1375, comma 1980. You know, I may have these up out of order. Not certain, but these are the 5 solutions, folks. They may not line up directly. I think I got this backwards here, because when you square this, you would get 9 times 55. See, yeah. When you square this, you get 9 times 55, which is this one, right? When you square this one, you get 64 times something, which would be, I think this one, 3520. Although that doesn't seem right. 55. Maybe, yeah, oh yeah. Okay. But yeah, I think the only 2 I got interchanged were this one and this one. So you see right here, folks, there are 5 as far as the way I've written it here. But notice this thing is completely symmetrical. Okay. So, you know, I could have kept running this list. The next element would have been 6 in front of this and 5 in front of this and so on. So we got 5 written down so far. So the answer is 2 times 5 solutions. Well, that's not quite right. There's 2 times 5 solutions, and the others would just be these swapped, okay? So there's 2 times 5 solutions. And I asked to list them all, but one, like for example right here, you would also have, corresponding to this one, 1980. And I'm just running out of room as far as writing it. 1980, comma 1375. Right? Okay. So again, yeah, apologies. I was trying to keep it all on one screen here. But there are 2 times 5 solutions, so there's 10 total solutions. I didn't ask for that. I asked to list the solutions. But something very interesting, I'm going to do a video on this too. Notice that this 10 is 11 minus 1. And that's true in general. So if you have a prime factorization with a signature of 3, 1, you're always going to have the exponent at 3, subtract 1 from that, and that'll give you the base exponent at 3 will give you the number of solutions. Okay, it's a fairly easy proof if you just write this down in the form p cubed times q. Okay, anyway, I hope this is readable and understandable. 10 solutions, I wrote down 6 of them. Okay, and again, I got the order backwards, I believe, somewhere along in here. Okay. So anyway, that's all, folks. Thank you for viewing.